Thank you, Nihar, and thanks to the organizers for giving this opportunity. So what I'm going to show you are only experimental results. Not much theory curves are there. But all of them you have already seen. At least today morning, all the results you have seen. So this is time to just relax and see some experimental data. And it's good if we can interact in between. And we'll stop wherever the time is up. So Nihar said that I should talk something on experimental results on heavy flavor and Quarkonia. So this is a slide which you have seen today morning, that heavy quarks, that means hadrons which are carrying a C or a B quark, are unique probes of Quark-Gluon plasma. And the reason is that they are produced early through initial hard scattering. Their formation time is of this order, and hence they experience the entire space-time evolution of the medium. On the theoretical side, because of their large mass compared to the scale of QCD, their production can be calculated using perturbative techniques. So that is good. You can measure something which is sensitive to the complete medium evolution, and then you can calculate it also. And what insight it brings, it tells us about how these photons lose energy in the medium. It tells us about the transport properties, degree of thermalization, and some of the measurement tells us how they are produced by fragmentation versus recombination. And so these are some things which we will discuss. The results that I will show come from two facilities. One is the relativistic heavy ion collider. We just stopped taking data. It is at this place, the electron ion collider, the previous talk that you saw, will happen, and that's why the data taking stopped after 25 years. So this is an aerial picture of BNL, Brookhaven National Laboratory, where this facility is. This is a collider with a circumference of about close to 4 kilometers, 3.8 or 3.5 to 3.8 kilometers. When it started taking data, there were 4 experiments. And by the time it ended taking data, one experiment remained consistently. The other got upgraded version came. So it's STAR and S-Phoenix. So today I will only concentrate on results from STAR experiment. This is also the only collider facility where we could have polarized proton collisions, which you heard in the previous talk. And this is a versatile machine where we could collide ions of different kinds up to uranium, also protons, proton deuterons, and with a variety of collision energies from 7.7 GeV per nucleon center of mass energy to 200 GeV per nucleon center of mass energy. So that's one facility. This is now the only collider which is running. This is the Large Hadron Collider. As the name suggests, this circumference is about 27 kilometers. There are 4 experiments. And the one experiment which is dedicated for heavy ion physics is called ALICE. And I will focus on only results from ALICE. But there are other experiments which also give heavy flavor measurements. They do it very nicely with excellent resolutions. These are CMS and ATLAS and LHCb, but I will not cover today those results. This facility primarily collides lead ions at energies of 5 tera electron volt per nucleon. And they also collide protons on proton and proton on lead. Recently, they collided also gold, no, not gold, oxygen on oxygen and neon on neon, small systems. And both have produced Quark-Gluon plasma. Now let me, I do not know, you must have heard during this week the time evolution of heavy ion collision. What are the things which happen when 2 heavy ions collide? So this is a pictorial representation of it. 2 heavy ions are coming from opposite direction and colliding. So they are moving with relativistic speed, and hence they are shown as Lorentz contracted along the direction of motion. So then they come and collide a large amount of energy is deposited in a small volume. Nuclear sizes are of the order of, radii are of the order of 6 to 7 Fermi. And so a large energy density is created. If a large energy density is created, temperatures can be large. Energy density goes as T to the power 4. And if the temperatures are large enough to melt a system into its fundamental units, the quark and gluons, we can form quark-gluon plasma. And this quark-gluon plasma happens through some initial phases, which is very important. Once this quark-gluon plasma are formed, then the system is expanding. When it is expanding, it is doing some work. As a result, some energy is invested, so the temperature falls. When the temperature falls a particular value, where quark and gluons can no longer remain free, because in nature you don't find free quark and gluons. Then they have to form hadrons, where quark and gluons are confined inside these particles called hadrons. Like protons and neutrons, these are kind of hadrons called baryons. And with quark and antiquark, these are mesons like pions, kaons. So that is called hadronization. Now, when this hadronization happens, the system continues to expand and interact. Then at some point, the inelastic collisions among the constituents stop. So no new kind of particles are produced. New type of particles are no longer produced. And that is what we call as chemical freeze out. The composition, particle composition, type composition gets fixed. The system continues to interact through elastic collisions, and a situation is reached when the distance between any two particles is much larger than the mean free path. Then no longer elastic interactions can also happen. They become free streaming and hit the detector. So on the detector, we detect these particles, and we have to use different techniques, ideas to figure out what all I told you really happened or not. The challenge is that all these happens in very short time and stays for very short time, and system is also very small. And to detect this, we need meter scale detectors, femtoscale systems, but to measure, we need meter scale detectors. So those are the complexities involved in this experiment, relativistic heavy ion collisions. Now, first, one thing is whether the system which is formed is thermalized. So there is a lot of arguments going on. What is the observable which tells the system is thermalized? I'll give you one example. This diagram shows that yields of different kind of particles. These are the particles which are produced in heavy ion collision. This is a particular example from ALICE experiment, lead-on-lead collisions at center of mass energy 2.76 TeV. You can see the red points are the yields, okay? Pions, kaons, so there are, these are mesons, there are baryons, some of them are neutral particle, charged particle, nuclei, strange particle, all these yields are there, and yields vary over 10 orders in magnitude. And the lines are statistical hadronization model, which assumes grand canonical ensemble. Basically, they can calculate numbers or yields if you know the volume, the chemical potential, and the temperature. And at LHC, the chemical potential, say for baryonic chemical potential is 0, close to 0. So you have only two variables, volume and temperature. Using only two variables, you are able to explain 10 orders of magnitude of difference in yields of variety of particles. These are the lines. And the temperature turns out to be around 155 MeV, whatever is extracted from here. Now, since this is related to heavy flavor, it turns out that these heavy flavor particles also are well described in such a model with a temperature very close to what you see for light quark carrying hadrons or nuclei. The temperature is around 156 MeV. So this is one way to show that it seems thermal picture is working. The other point I want to tell you before I go to the results is it was predicted, it was told today morning in this paper that if you form Quark-Gluon plasma, then what would happen is you will find a phenomena called as screening of charges. As a result, in order to form particles like Jep psi, which are bound pairs of CC bar, you need C and C bar to come together and form these mesons. But if in intermediate space there are other quarks like UD quarks, then you cannot form Jep psi. So the Jep psi production will be suppressed. And one way to look at this suppression is to calculate the nuclear modification factor, which has been explained in previous talks. This is yield in heavy ion divided by yield in proton-proton collisions, appropriately normalized. As a function of multiplicity, this is head-on collisions, large multiplicity. These are peripheral collisions or grazing collisions. And what you find is data from lower SPS energy, center of mass energy 17 GeV. Then RHIC, relativistic heavy ion collider, 200 GeV. And heavy ions at LHC, 5 TeV. And you can see in general, the Jep psi production is suppressed. If it would have been 1, then there is no suppression. What is interesting to note that as you go to higher and higher, denser and denser medium, one would have expressed more and more suppression. But there is a counter phenomena occurring, which is regeneration through recombination mechanism, which happens to be more as you go to LHC energies. So that is why you see this pattern. But in general, we see this suppression of Jep psi in heavy ion collisions starting from SPS, RHIC to LHC. Okay, so with this little brief introduction, let me go to show you some selected results. First from RHIC, and I will only tell about star experiment.
This light nuclei, how does this thermal model predict the light nuclei pattern? Because we need some interactions to predict, to get this light nuclei.
Yes, yeah, it's a fit to the data and it fits well. So what he's saying is, in this model, there are many simplifications. It's a non-interacting set of particles formed in a box, in that way. But it turns out that it is explaining this. Although we know that some of the assumptions that we make may not hold. But it's surprising that it holds here. Now, let's come to some results from RHIC. So this is a typical experiment. Again, you saw today morning about star experiment. You saw about HFT and this. So I will not spend much time on this. But I want to tell you that only 5 kind of charged particles are stable enough to reach our detector. They are muons, electrons, pions, kaons, and protons, plus and minus. And only 2 kinds of neutral particles, that is photon and neutron. We don't detect neutrinos. With this, we try to do the physics that we see. Of course, we can get its momentum, special distribution, and other things. First thing that we will discuss is about charm-strange meson production. So this is the D mesons, okay? What you have seen, you saw in today morning, this is how we reconstruct these D mesons, D plus minus and D plus minus with sub S, okay, through the invariant mass of their decay daughters. This is the momentum distribution of these particles. Now, the idea is, what is the thing that we were looking for when we made these measurements? In a typical PP collisions, you would expect that fragmentation is the process by which these are produced. That is, a charm quark fragments to D, D plus minus, or DS. However, if there is a Quark-Gluon plasma, then you may also have additional mechanism of formation of these charm mesons through coalescence process. So what we are, and if there is QGP, then you should have abundant strange quarks, and that would lead to a production of DS, which is much more than what you expect in, say, PP collisions. So we would ideally look at an observable DS by D0 in heavy ion and PP. and we want to see in heavy ion, is this enhanced? That would be a signature that, okay, they are produced through coalescence and maybe the medium has Quark-Gluon plasma. So this is an observable. This has a strange quark. This is a light quark and a charm quark. We measure this ratio in heavy ion. We measure this ratio in PP. Our expectation is if there is recombination in place and QGP formed, this in heavy ion should be enhanced compared to PP. And that is the result shown. Here the PP reference is, you see, this is the DS, this is D0, and the PP reference is given by Pythia here. Of course, we have PP data at LHC, which follows the Pythia, and you find that it is enhanced. So heavy ion collisions like gold-gold collisions or lead-lead collisions, this ratio is more compared to proton-proton collisions. So the simple physics interpretation is charm quarks recombine with strange quarks in a partonic medium, modifying how the heavy flavor hadronizes. This is one indication from the measurements given that expectation. Now what about baryons? Those were mesons. Now in baryons, for example, lambda C, will this measurement tell us something about charm baryon production? Now in elementary collisions again, they could be produced through fragmentation, and from these elementary particle or PP collisions also, it has been seen that lambda C by D0 ratio is of the order of 0.1. Now again, in heavy ion collision, if there is a Quark-Gluon plasma formation and coalescence is in place, then you could find additional ways by which lambda C can be produced. So if you measure a baryon to meson ratio in the charm sector, lambda C by D0, then this should be enhanced compared to proton-proton collision. So this measurement, but by the way, this is a complicated particle to get because it decays to kaon, proton, pion, and all the three fall on a detector. Depending on the momentum range, it is difficult to identify which is kaon, which is pion, which is proton. So it's very challenging measurement, but it has been measured. So this is this baryon to meson ratio. This red points, this is from RHIC, lambda C by D mesons, and this is the same data as a function of PT with different models. So what do you see? You see that lambda C by D reaches a value of order 1. Whereas PP collisions or models through fragmentation process without coalescence, without Quark-Gluon plasma lies somewhere here. Okay. So again, you see, just like the meson sector, here in the baryon sector, it is enhanced compared to proton-proton collisions, the heavy ion collisions. Not only is it enhanced, these values are similar to what we had seen in strange sector, the lambda by K shot, or in light quark sector, the UD quark sector, proton by pion. They are very comparable. That's what.
So if you look at the light sector, ratio drops down. Can we say the same because there is no ratio?
What I'm saying is the order of magnitude is same in the measured region. I don't have measurements, so I cannot say, but okay.
If it also goes down, then ratio might be less than.
Of course, but the ratio is 1 in a particular region where coalescence is expected to work. Okay, so that is also what we saw, meson and baryon sector. Now let us see the suppression of D mesons. Now this is that observable which you have seen in the morning, and this observable simply tells us if heavy ion collision is a simple superposition of many PP collisions, then it should be 1. If it is not, then it should be different from 1. And if the quarks lose energy in the medium, then this should be less than 1. So that is this quantity, RAA, plotted as a function of impact parameter or of the collision. Large values of this variable, number of participating nucleons, means head-on collisions. And small values means grazing collisions. These means more denser medium. You expect more suppression because you have high temperature, more probability to form QGP. And here it is more proton-proton-like because it is a small number of participating system. And then what you see from the data in two different momentum ranges, indeed, there is a pattern and it is suppressed. The value is of the order of 0.5. So charm quark seems to be losing significant energy in the QGP. And the suppression levels are very comparable to what you see in other particles like pions or other mesons. Now, what about things which involve bottom quark at RHIC energy? So these are upsilon states, right? Now, people say that, I mean, the theoreticians suggest that depending on the temperatures which you reach in the collisions, you should see a pattern in this suppression of production in the upsilons, okay? That is related to how they are bound. This is more tightly bound, this is intermediate bound, this is weakly bound. So this should be more suppressed compared to this, if you make an experimental measurement of the same nuclear modification factor of upsilons, which are BB bar bound state. So that was also done in star, okay? This is that same nuclear modification factor. X-axis is again same. This is head-on collision, more denser system, hotter system, QGP formation probability more. This is less, peripheral collisions. And what you should see is the red, blue, and green. Is there an order? Indeed, there is some order. We are, with the statistics available, we have put a sort of an upper limit. That's why you can see this arrow. The value will be somewhere here or lower. That's the upper limit. So what you see is the one which is tightly bound has an RA of 0.4. The intermediate bound is 0.26. And then the RA from whatever data we have tells us that upsilon 3s has to be lower than 0.17. So indeed, we see a pattern in this BB bar suppression at RHIC energies. Now, coming to flow, the elliptic flow, this is another observable which was discussed in the morning. It is calculated by measuring the azimuthal angle distribution of these particles of interest with respect to reaction plane. The reaction plane is a plane which is subtended by the impact parameter and the beam axis. But impact parameter in a collision, we cannot measure. So there are ways to get handle of this psi 2 and correct for it so that it resembles as close as possible to the reaction plane. But the observable is V2, okay? And also you heard that the V2 is developed only if there is interaction of these particles that leads to a large V2. So do charm quarks also interact sufficiently with the medium that they acquire collective flow, and do they exhibit collective flow? So the measurements have been done. These are for D mesons. Okay, I'll go to the next slide to show you the result. These are D0. This is the charm quark, okay, carrying meson. And these are other light quark carrying mesons, okay? And the blue points are charm quark carrying mesons. If you divide the X and Y axis by the number of constituent quarks, for a baryon it is 3, for a meson it is 2, then they all fall on one line. This is what is called as the number of constituent quark scaling. Now, why that is an important view from the experimental point of view is that, you see, I mean, there are also pions, protons, kaons. We can put everything here. They are all seems to be following one pattern. Of course, you can tell to what percentage, 5%, 10%, but it's remarkable that starting from D mesons to lambda baryons to kaons to pions to protons, why should they follow a common curve? Unless the origin of their collective behavior is also common to everyone. And the thing which is common is they must have come from a partonic source. So that is why people get very excited, or experimentalists, that seeing this type of scaling and associate this to collectivity originating from partonic level or the Quark-Gluon plasma level. So indeed, we see a strong elliptic flow for D mesons. And if you put theoretical curves with different values of diffusion coefficient, then you find that within the uncertainties, they give you a value of this dimensionless quantity for charm diffusion coefficient between 2 to 12. These are also consistent with the lattice results which you saw in the morning. Okay, but what about, remember, D meson has a light quark and a charm quark. But what about systems which has only charm quark, like JEPSI, CC bar? So you can do the same measurement and we find that it is 0. JEPSI V2 as a function of PT for different collision centrality within the uncertainties are 0. Let me show you one more plot. Okay, this also tells you the same thing. You see, these are different meson. This is charge hadron, this is phi, and D0 meson also goes in the same way. But these black points are JEPSI, CC bar. They somehow seem to suggest that they don't have any flow and they're not sufficiently interacting to generate flow. Maybe their production is dominated by mechanisms which are other than recombination. That is what these measurements tend to say, but you remember the error bars are also large. Keep this in mind because you will see different thing at LHC energies. Okay, what about directed flow? Directed flow, again, instead of that 2 here, there is no factor 2. It's not elliptic flow. This is directed flow. Otherwise, the expression is same. Now, this is there is an interesting proposal that when two heavy ions come and collide, then there is a participating region which is involved, whose interactions leads to particle production, and then there is a spectator regime. The spectators are mostly protons and neutrons which didn't interact and go away. But among them, the protons are the ones which are carrying charge and moving with relativistic speed. So a charge particle moving with relativistic speed will produce large electromagnetic fields. So, and since heavy hadrons, heavy quark carrying hadrons are produced early, they should experience maximum this kind of electromagnetic fields. That is one way of looking at it. So trying to find out directed flow will give a handle on that. There are also suggestions that, this system which experiences hydrodynamic evolution, if the QGP source is tilted, then also you will get a V1, which is given by this expression, measured in experiment, should be much, much larger for D mesons than for light hadrons. And that is what was observed. This is the V1 of D0 and its antiparticles, which are shown here. Let me see if I have a, yes, it is there. So this is V1 of these D0 plus D0 bar, just to increase the statistics. And this is what you see for light quark carrying hadrons, okay? So it is 25 times this V1 is larger compared to light quark carrying hadrons. Now it is suggested that you look at the difference in D0 to D0 bar. Again, that is sensitive to both the tilt of the source and electromagnetic fields. Heavy ion collision seems to be complicated by many phenomena altogether. So finding a good observable, how to constrain different things is the key. Okay, so you saw earlier in the morning where Santosh told about how you can extract electromagnetic fields. In the talk next, you will see same plot which will talk about how tilting of the fireball can also give a contribution. But remember this slope, LHC results, when I show it's a different one. Now, there was mention about EIC. So one result, RHIC is now going to become EIC. So there are measurements which are related to that. We have measured JEPSI at high momentum, but we also, with clever data analysis, have measured JEPSI below 200 MeV. Okay, and then we find that simple extrapolation in the lower PT doesn't work for that. This production is enhanced by almost like factor 25, 30. This Y is low PT JEPSI in just, I mean, this is uranium collisions enhanced so much. Okay, so there must be additional particle production mechanism. Remember, these are not ultra-peripheral collisions. These are just heavy ion collisions, but we are able to measure JEPSI at very low momentum. So, for example, if you look at RA at low PT, they are factor 24 in peripheral gold-gold collisions, 52 in uranium-uranium collisions. So this was a very interesting measurement which was done. People suggested that they could be related to what is called as coherently produced JEPSI at low PT. I'll come to that. And if that is so, then we have started thinking that then there could be interesting probes about how the gluons are distributed in the systems which we collide, and they could also be novel probes of QGP. So now the best way to look at coherent, incoherent production is using ultra-peripheral collisions. So what is ultra-peripheral collisions? Ultra-peripheral collisions, if you have A and B nuclei coming and colliding, you look for collisions where impact parameter is greater than the sum of the radius of the two nuclei. So you don't expect any hadronic interactions. These are generally mediated or it's through photon process. This is the diagrammatic representation of this. Now there can be two kinds of production processes. One is coherent and the other is incoherent. In the incoherent process, this nuclei fragments into different particles. Coherent, as the name suggests, the nuclei as a whole seems to be interacting with the incoming photon. Again, depending on this size, you can find out where coherent will dominate, what momentum of photons will tell you where the coherent process happens. And why these are important? Because they are important, as you heard in the talk just before, that they are important to tell us about the gluonic structure of the other nuclei and gluon density and things like that. So we have measured this JEPSI produced through the process where there is ultra-peripheral collision. A photon coming from a nuclei interacts with the deuteron, produces JEPSI, and if X is the deuteron, then it's coherent. If it fragments into other particles, it's incoherent. And this is the result. This is the cross-section as a function of a quantity which is PT square. It's called as minus T. And this is neutron tagged. That means the deuteron has broken up and we have tagged the neutron coming from the deuteron. So that means this is incoherent. And the black ones are the total. And then you can get the coherent data of coherent JEPSI produced. And those can be understood using different, they can give you idea about gluon density. There are models like CGC, which seems to be explaining the data better compared to shadowing models. So there are a lot of things which you can do with this data. I'm not going into the models. I'm just telling you what we did in a measurement. We are able to tell you incoherent, coherent production of JEPSIs. Same thing we could also do in gold-gold collisions. Again, ultra-peripheral collisions. We can measure the yields of the cross-sections in coherent process, incoherent process, and whether there is no neutron produced, one neutron produced. Many different combinations can be tagged in the experiment, and we can measure the JEPSI produced in these different processes. And this, when compared to theory, will give you information about the gluonic content, the distributions of the things which we are colliding. Okay, I'll skip this. So let me now summarize what we found at RHIC only from experimental point of view. Remember that heavy quarks are probe of multiple aspects of QCD matter. They tell about transport property, early time collision geometry, hadronization, production dynamics. What we find in the early time is the D0 V1 is much, much larger than light hadrons. This is showing that maybe it's a tilted initial geometry of the fireball. What we found is both ds by d0 and lambda c by d0 are enhanced in heavy ion compared to PP collisions, telling there is QGP formation and coalescence is the process by which hadronization happened. This I have not shown you any results, the third one. We also saw that D0 production is suppressed. The RA, nuclear modification factor, so charm quark energy loss we saw. We found D0 has finite, a large V2. However, JEPSI V2 turns out to be 0, and with the current uncertainties at RHIC. So all taken together, RHIC measurements show that heavy quarks interact strongly with QGP, participate in collective dynamics, and hadronize through recombination with the medium quarks. That is from RHIC. So whatever little few more minutes I have, I will now show you LHC results. And again, I will concentrate only on ALICE. Okay, but there are very beautiful results from CMS, ATLAS, and LHCb. This is ALICE detector. You can see, I was telling you the scale. This is the typical height of a person, and this is roughly 26 meter high. It is 50 meters underground, and we have almost 19 detectors, sub-detectors, which make a large ion collider experiment, ALICE, together. And what we do with this system is we can measure all these different kind of particles in this momentum range. Okay, like protons, pions, kaons, nuclei, photon, pi zero, eta, d meson, you can see. Omega. So these are all the particles that we can measure using many, many different kind of techniques, the detectors in this momentum range. So that allows us to probe QCD matter in a temperature range starting from 100 MeV to 801 GeV, where mu B is 0, net baryon free, and alpha S seems to vary from 0.1 to 1 if I take some crude estimates. So this is a beautiful experiment. They reach directly to the detector. We use, so they decay to these particles, and then we use invariant mass and decay topology to construct it. Okay?
What is the initial temperature that is usually considered for the ALICE case?
Around 800, 900 MeV, close to it. GeV is what, when you match hydro with initial conditions to the data, tends to suggest this order. Okay. So let us come back to, so then let's start with charm baryon. Remember this quantity, okay? This quantity should be more than PP in heavy ion collisions at RHIC. What happens at LHC? And here is, LHC, what happens is the fireball remains for a longer duration, and hence the yields are large, as well as the kinematics reach are also large in PT, in acceptance. So keep that in mind. And what you see, here are the, where are the Pythias, yeah. So here are the Herwig, and this is Pythia 8 with a particular mode. And you can see that this lambda C by D0 values are much larger compared to what is expected from PP collisions or from fragmentation model, almost factor 3 to 5. But what you see is standard fragmentation is unable to explain the data for charm baryon production at LHC. So this data can also be used to improve this, along with some other maybe correlations or things to get a handle on how to explain baryon production in this sector in models like Pythia. And this is data from PP collisions. Remember, this is data PP collisions, okay? This is already at LHC, we are not able to explain. Now, when we put in P-led collisions, you can see here P-led data. And of course, this is PP data. And you can see that the P-led collision data is very comparable to what you see in baryon to meson ratios in the strange sector, or this is lambda by K short, okay? And this is for PP collisions, this is proton pion, and this one is lambda K short, and this is lambda C by D0. So what it seems is that from this data taken together and with different kind of model approaches like coalescence, statistical hadronization, or fragmentation, it seems charm hadronization in hadronic collisions is not universal, and there are effects which would involve collective effects or recombination mechanism which is affecting their production. That is seems to be what is happening at LHC. What about sequential suppression? So here is a result of GEPSI and Psi2S. Okay, remember these are the typical binding energies. So you would expect, because of these binding energy values, Psi2S should be more suppressed compared to GEPSI. So this is the nuclear modification factor as a function of collision centrality. These are head-on collisions, dense matter, peripheral collisions, grazing collisions. This is data which is shown for GEPSI, and this is Psi2S. And indeed, you see that Psi2S is more significantly suppressed than GEPSI. Similar observation as we saw at RHIC. And this is again similar, I mean the same results, but what we have done is there are CMS results here to just show that there is consistency, and Psi2S is more suppressed than GEPSI. The value of RA is of the order of 0.4 for Psi2S, and GEPS, which is stronger than for GEPSI at high PT. So that is what we see. Now, what about flow? I showed you at RHIC D0V2, and D0V2 was very large, and it was comparable to other hadrons. At LHC, we are able to measure D0, D plus, D star, DS, all the flows, and V2, which is this quantity, and all of them seems to have large finite V2. What's the conclusion? Conclusion is that similar to that of at RHIC, that we have large collectivity seen in case of D0s. So that means charm quarks develop significant elliptic flow. This is an evidence of their strong coupling between heavy quarks and the QGP medium. And if you confront it to theoretical models, which has different values of DS, the DS diffusion, heavy quark diffusion coefficient, then this dimensionless quantity seem to be constrained to be between 1.5 to 7. That is what we observed at LHC. Similar order as at RHIC. Similar conclusions as at RHIC. What about GEPSI? Remember at GEPSI, CC bar at RHIC was 0. GEPSI within the uncertainties as a function of PT. Here is V2 of GEPSI, the red points, and this is as a function of PT, and you can see that it is non-zero. Okay. Now, if you want the significance, it's 6.6 sigma significance in a PT range of 4 to 6 GeV. This is again GEPSI V2. There are different collision centralities, and the largest deviation data is 6.6 sigma away from 0. So this is something different compared to what we saw at RHIC. RHIC, GEPSI, CC bar, V2 was 0. Here it is non-zero. It is quite large, almost 0.15 of that order. Now, let's see. No, okay, let me go to, so immediate interest is if CC bar is now non-zero, what about BB bar, the heavier quark? So let me not go to the, okay, let's come to the V2 of upsilons. Okay, these are BB bar. GEPSI is CC bar, charm meson. And this is bottom BB bar. And what you find is, while GEPSI is non-zero, V2 as a function of PT, the BB bar seems to be 0. So that is what, but again, you know, uncertainties are large, and we have taken a large amount of statistics. We'll try to see what it is, what is the real picture when we analyze the run 3 data.
Is it
well, then we have to see how the, I now don't remember what was put in this into this model. So we have to see what it. Okay. So this is another way of putting it. V2 as a function of collision centrality. These are violent collisions. These are little less violent collisions. BB bar or upsilon in this PT range, in this forward rapidity is 0. J psi is non-zero. That is one thing that we see. Okay, this is the summary of flow of all the particles that we see, from pions to d meson to J psi to beauty coming. There's a semi-leptonic decay of beauty carrying hadrons or upsilon, all put together is the flow. Now about the V1 measurement. Okay, this is the same measurement V1 of d mesons as a function of rapidity, and so this is the red point is d0, blue point is d0 bar. You saw this kind of picture at RHIC. Okay, now this is lead-lead collision at 5 TeV. Now when you take difference, instead of this going like this at RHIC, it is going opposite at LHC. Okay, now this has generated a lot of debate. So this has generated quite a bit of debate. What could be the interplay of different mechanisms to explain this? But I must say we are also reanalyzing this with a large data set and trying to find out what it is. I cannot reveal what is going on, but anyway, so you please look out for this. We are double checking a lot on this measurement. But these are sensitive to initial stage effects, whether it's the tilt of the source or electromagnetic fields. Go ahead. This is difference in V1 of particle and antiparticle. You remember when Santosh was showing that charm and anti-charm quark will have a different, because they are particle and antiparticle to electromagnetic field. So that's the reason we take a difference to see whether what theory says we observe a similar trend or not. We have sufficient data to go to lower petals. But it will take some time because okay, it's getting recorded, but obviously if it would have been exactly along, then we can. So it's going on. Okay. Now what RHIC really, LHC brought in is another dimension of polarization of J psi. That is a very interesting measurement. Now polarization, how much? 40 minutes? 2 minutes, okay. So polarization is another interesting observable which has come into in the current scenario. One of the reasons why it can happen is because of spin orbital angular momentum interactions. Okay. Now the way you measure this polarization is you have to have a sort of what is called as a quantum axis. That is you have to know the direction of angular momentum or the magnetic field, and then you have to measure the angular distribution of the decay of say vector meson, the angular distribution, the angle made by this decay daughter with respect to this quantization axis or direction of magnetic field or angular momentum. And that is sensitive to whether there is polarization or spins are aligned along the angular momentum direction. So if there is no polarization or the spins are not aligned along the direction of angular momentum, then angular distribution will be flat. If you plot cosine theta and the yield dn d cos theta, it would be flat. If it is non-flat, that means there is a polarization or a spin alignment. So that is the experimental way of looking whether the system is polarized or it has a spin alignment. So you can already guess what I'm going to tell this. You can see this distribution is non-flat compared to where we know that there is no polarization. And you can extract a parameter which defines polarization. If it's 0, it's not polarized. And you can see a 3.9 sigma effect of J psi getting polarized in lead-lead collisions at 5 TeV. Similar measurements has been done. This is now spin alignment. It's analogous quantity for D star mesons. Now, it's a spin 1 particle. So it can have spin states -1, 0, 1. All are equally probable. So the probability is 1/3, 1/3, 1/3. But if the spins are aligned, then the probability won't remain 1/3, 1/3, 1/3. So it will be different from 1/3. So this measures what is the probability of finding D star in spin state 0. Okay, so it should be 1/3, but there is some deviations. Okay, let me go to the, you can see there is clear deviation from 1/3 value of the probability, which if there is no alignment, no polarization, it should be 1/3. And this is again, the error bars are large, but it's again a 3 sigma effect that we can say that there is something going on. So there are these interesting measurements which are coming up in the polarization and spin alignment sector. Okay, I will not go into the coherent, incoherent aspects are also studied at LHC energies. So let me summarize. Again, you know why one is interested to study heavy quarks in heavy ion collisions, but also remember that it has a great role to play in spin physics. The hydrodynamics is not only relativistic viscous hydrodynamics, it's relativistic viscous magneto spin hydrodynamics. So it's a completely evolving field, how to incorporate magnetic field and spin effects in the hydrodynamics, in relativistic viscous hydrodynamics. What we find is there is spin alignment observed at LHC energies. What we find is D meson is suppressed. There is heavy quark energy loss. There is collective expansion. There is enhancement in these ratios. We find that Jepsi suppression is weaker at LHC than RHIC. This is because of regeneration. We find Jepsi elliptic flow at LHC is non-zero. RHIC it was 0. Okay. And of course, there is a spin alignment seen. Okay, those are some of the results. Thank you very much for your attention.
Thank you very much for this nice presentation. Okay, so now for question. Yes, please.
Do we have any measurements at RHIC energies for PP, lambda C? So because you said that there is enhancement.
No, we are taking Pythia as the baseline. We don't have.
Okay.
But I'm not ruling out that we will not have, because we also took a lot of PP data, but at the moment we don't have. Okay. That's why the baseline was PP. But if you see that plot once more, just I'll quickly go there. Pythia is doing well in that observable where LHC has data.
Yes. Yes.
So yeah. We are, where did it go? Oops. You see, these are PP data and Pythia is here. So in that sense.
So the second question I had was, so when we, like theory people calculate V2, how to make sure that, because the V2 that we calculate, we just like convolute over like convolute the phase-space distributions over cos 2 phi.
It's theory.
Yeah, theories. Okay. Sorry. But the V2 measurements are done with respect to the event plane. So how to make sure that when we calculate, we are calculating the same thing that experimentalists are measuring, so that we have the right data to theory comparison?
Well, you do event by event hydrodynamics? No.
Currently,
not.
No. So
the best thing would be to do event by event hydrodynamics, because this is event by event measurement. Our measurements, we cannot really get that reaction plane. So what we get is an event plane. Now that event plane, how well we know depends on the amount of flow. If there is large flow, then many particles are going in a direction, so we know where is the direction. And also it depends on the number of particles. If there are larger number of particles, it's easy to figure out the direction. So with those caveats, we do correct for it. We assign uncertainties for it. And plus, there is something called non-flow. So that also we try our best to take care of it. So that way it is a okay comparison if you are taking our uncertainties seriously. That is what I would say.
Question?
Huh.
RA that you showed between the uranium and
Achha,
that,
UPC.
which was very high.
Not UPC, but low PT.
Mid central, yeah,
Ah,
here.
yeah.
You said that it becomes large.
This is RA.
Yeah.
This is uranium. The circles are 40 to 60. More peripheral is 60 to 80. And they are all above 1. And this is also gold. Gold is also there. So, but at high PT, it is suppressed. Low PT, it's.
Oh, okay. So gold and uranium both are showing similar behavior. Okay.
Magnitude is different, but enhanced. So then maybe that is coherent production is what one is thinking, but I don't know if you want to explain the data would be good.
Any other question? Okay, I have one. Okay, so in this conclusion part, you indicate for D meson at RHIC and LSC, of course, finite 10 to 15% strong flow, both RHIC and ALICE,
Right.
and that we understand strong collectivity. But when we look at charmonium, LSC at RHIC it is 0, although D meson has quite strong, but LSC still D meson are some similar order, but charmonium is quite comparable. What is the possible any thought?
The thought I have written, I told this is the reason. Charm quarks partially thermalized in the medium. And maybe they are also produced by method of recombination. Maybe that is what it is adding to the V2, high V2.
Okay, because in one case it's 0, another 15% around.
0.15. 0.15 it is going, yes. Regeneration could be one reason, but that only when you start comparing to our data, you will get an idea what is going on.
Any other question? So if not, let
Thank
them
you.
thanks the
Thank
speaker
you
once
very
again.
much.